know this input impedance of the transistor is given by HIE plus 1 plus HFE into ZE. And 1 plus HFE is coming because it is IE, and IE, I'm going to write it as IC plus IB. So that simplification we have done lot of times in the previous classes. So whenever you have a resistance RE, it will be multiplied by 1 plus HFE, because the current flowing through RE is IE. IE is equal to IB plus IC, and IB is equal to beta IB. So when you substitute all the simplification, you get RI is equal to HIE plus 1 plus HFE into RE usually you will get, but here it is ZE. What is ZE? Parallel combination of RE and the reactance of the capacitor. The capacitive reactance XC is given by 1 by omega C. So you apply the parallel formula. Okay, so apply the parallel formula 1 by omega C. So RE into 1 by omega C divided by RE plus 1 by j omega C. So when you take LCM, you get RE by 1 plus j omega CE into RE. So this is the reactance present at the emitter side of my transistor. So step by step, you have to do and cross check. Okay, so whatever I teach, you have to manually work out this simplification of parallel resistance and see whether you are getting this expression. Okay, so when this XC is 1 by j omega C, if you substitute here, it is RE parallel to 1 by j omega CE. So RE into 1 by j omega CE divided by RE plus 1 by j omega CE. So when you simplify and take LCM, you get RE by 1 plus j omega CE into RE. So substitute this value of ZE in the expression for RI. So RI equal to HIE plus 1 plus HFE into this term, RE by 1 plus j omega CE into RE. And substitute this is RI in the expression for IB. So this we started with IB. From IB, we are finding out what is RI. From RI, we are finding out what is ZE. Then just do the reverse step. Substitute ZE expression in RI, substitute RI expression in IB. So when you substitute the expression of RI in IB, you get this one. IB is equal to VS by RS plus RI. And RI is going to be this big expression, HIE plus 1 plus HFE into RE by 1 plus j omega CE into RE. Now substitute everything in V naught. So V naught equal to minus HFE into IB into RL. And V naught by Vs is going to be the voltage gain. So AVLF equal to V naught, divide both sides by Vs. V naught by Vs, when you divide, you get minus HFE RL by this big term. Minus HFE RL by the big term. Any doubt so far? See, step by step we are doing it. Any doubts so far you have in the derivation of AVLF, and why we are doing it is we are going to find out what is the effect of CE on the low frequency response of the amplifier. So for that we have included CE in the circuit parallel to RE, and wherever we are finding out the resistance at the collector, we are going to do RE parallel to CE. That is what you've done in the derivation, and we are calling that term by a simplified term ZE. Okay, whenever you have only RE, you call it as emitter resistance. When you have RE parallel to CE, you call it as emitter reactance. That is why we use the term ZE. ZE is reactance present at the emitter side. Okay, and usually this RE will not come in the circuit because CE will be short circuited. But here CE is not short circuited because we are going to study the effect of CE. So you should have that CE in the circuit. That's why we have retained CE in the circuit. So in the mid-frequency range, your omega, the gain is constant. So you can, when you substitute the mid-frequency range, it is going to be constant. So constant means all the variable terms will not be there. So minus HFV RL by RS plus HA, this entire term will become 0. Because this is the only variable term having omega. Omega is frequency. The mid-frequency the gain is constant, right? So the second term will not come. So AVMF equal to minus HFE RL by RS plus HIE. So now find the ratio of the two frequency, two gains, AVLF divided by AVMF. So divide this term by this term. So when you divide, you get this expression RS plus HIE by RS plus HIE plus 1 plus HFE RE by 1 plus j omega CE into RE. So I am just multiplying and divide. I am just using the two frequencies F0 and FP here. So see here what is F0. F0, I am using F0 as 1 by 2 pi CE into RE. and FP is this big term, 1 plus HFE RE by RS plus HI divided by FE into RE. So I'm using this F naught and FP in the simplified equation so that I can eliminate all the big terms. So when I use that, I'll get this one. See, these things, derivation step by step is not required. You may even write the final step also. So when you simplify using substituting F naught and FP, you will finally end up in this way. Finally, this will be the formula for AVLF by AVMF. RS plus HIE by 1 plus HFE RE into JFP by F naught by 1 plus J. So you may even remember this expression for comparing the effect of CE on the low frequency response. So all the intermediate steps can be neglected. You can write for till AVLF, AVMF. You can divide them and finally you can write this expression. You can neglect all the intermediate steps. Simplification is just not required. Okay. And when you take modulus, so when you take modulus, you know this real numbers won't have modulus, and you see j fp by f naught. If you take modulus, you get fp by f naught, and modulus of 1 plus j is root 2. So you have this expression, and fp by f naught and these terms will get cancelled, so you get the answer as just 1 by root 2. So at this ratio, the voltage gain is dropped by the fraction of 1 by root 2, so it is called as 3 dB frequency. So the 3 dB frequency is given by this expression. It is equivalent to fp. Okay, the 3 dB frequency, whatever we assume two frequencies f naught and fp for simplification, right? So the 3 dB frequency is given by fp. So when fp equal to f naught, this condition